Hi folks, Buckley here. We're going to work through two 3D rigid body equilibrium problems. Just a warning, these feel like a bit of a heavier lift, okay, so hopefully this is coming in time for you to be working on these problems on your homework. Okay, so first one here, determine the components of reaction acting at the smooth journal bearings A, B, and C. Okay, so we're looking for what's happening at these three bearings. They're journal bearings. Okay, and what we know about journal bearings is that they're going to allow for spinning. They would allow for spinning, and they would allow for motion along the axis of the bearing. Okay, so basically, if this were a bearing block, all right, and there's a shaft coming out, it would be able to move like this, and it would be able to spin. We'd be able to have both things happening. The other thing to notice about this is we have these bearings. These bearings support each other, okay? So we mentioned that when you've got instances where you have bearings that are supported, we don't ask the bearings to support a moment, right? So they don't support off-axis moments, meaning I wouldn't try to induce a moment here about, let's see, the y-axis, nor would there be any about the x, or I'm sorry, y-axis, there would be a free spinning moment about x or about z. Okay, so we'll get into that in just a second, but we know a lot about these bearings, and that's actually the key to this problem. Given the diagram, given that these are smooth supported journal bearings at A, B, and C, I'm going to be asked to solve for the reactions at A, B, and C. And we'll get into what those are in a second. Okay. So also, guys, I hope this is working out. I actually upped the resolution on my camera here, so hopefully you're able to read my writing a little bit better. Please do let me know if there are any issues with watching my videos. I want to make sure that you can see everything properly. Okay, so let me start with the free body diagram. So I'll start by just kind of redrawing my axes here. So I've got Y, X, and Z. And I'm going to go ahead and sketch. Here's point A. I'm going to come down along the y-axis from A until I hit point B. So I'll call that A. I'll call that B. Extends a little bit further than B, and then it goes up in the Z direction to this point here. I'm going to go ahead and give that point a name. I'm going to call this guy point O. And at point O, we've got a force that's acting. I'm going to give that force a name too. I'm going to call it F. I know its direction and I know its magnitude, so more about that later. And then I'm going to go back in the negative X direction until I hit point C, which is another journal bearing. So journal bearings at A, B, and C. I've got something here with a force at 450 newtons acting here at point O. And then I'm also going to have a 300 Newton meter moment. I can go ahead and immediately say that that moment, which I'll call, let's say, moment P, or whatever, okay, it's a couple, is going to be equal to, and I know its direction, right, so that's going to be a negative y, right, so it's negative 300 in Newton meters in the j direction, right? Okay, and I'll go ahead and just define F for a second too, so I've got that as well. So F is 450 newtons. There's no component in X, so it's 0 in the I direction. It's going to be positive 450 cosine 45 degrees in the J direction, and negative 450 in the sine 45 degrees in the J direction. So I go ahead and I have that. So this will give me F is equal to 0 I plus 318.2 J minus 318.2 K. And these are all newtons. Okay, so just so you know, and I'll actually clarify this too, I'll say MP is equal to 0 I hat minus 300 J hat plus 0 K hat. Newton meters. So my MP and my F, I'll just go ahead and draw that as two vectors here just to keep it consistent. MP and F, the couple moment and the F there are fully defined by what's presented in the problem. Okay, now I'm ready to kind of tackle what's happening at my journal bearings here. Again, my journal bearings are supported, so what that tells me is that the moments off axis from the bearing are going to be 0, and this is allowed to spin as well, right? The only bearing that's not allowed to spin is a square bearing, so this is allowed to spin, so its moments everywhere are going to be 0, right? So one thing I know here is MA, the moments at A are actually 0, the moments at B are actually 0, and the reaction moments at C are actually 0. So I'm going to go ahead and put that on there. The only thing that's happening here is that I can't move this at A in the Z direction, so I have a force AZ, and I can't move it in the X direction, but I can move it in the Y direction theoretically at A. So I have an AZ and an AX, but AY is equal to 0. At B I have the same thing. I'd have a BZ and a BX, but BY is equal to 0. And at C, I would have, in this instance, CX would be equal to 0, but I would have a CZ and a CY. Okay, so that's my full free body diagram there. If I want to clarify, I would say here that CX is equal to 0. I would say here that BY is equal to 0. And I would say here that AY is equal to 0. This is making full use of what I know about these bearings. They're supported journal bearings. Okay, that is a correct free body diagram. It's a lot, right? But let me count up a couple things here. So I have 1, 2, 3, 4, 5, 6 unknowns. So I have 6 unknowns in this free body diagram. Fortunately, right, I have 6 equations that I'm going to be able to come up with. So I can actually solve this whole system. If I didn't know everything about these bearings, if I didn't know that they were supported, or I made a different assumption about what was going on with this journal bearing, I'd have a different kind of problem, right? Okay, and I might have a problem that I couldn't solve. So let me start now with, now that I've got my free body diagram done, I'm going to do my equilibrium expression. So I'm going to start with sum of the forces is equal to 0. And again, remembering that all my forces are A plus B plus C. So what's happening at A, what's happening at B, what's happening at C in terms of reactions from those bearings, plus F, right? Plus this force acting here. So if I split that out into what's happening in X, Y, and Z, I would get sum of the forces in X is equal to 0. I have here an AX plus a BX. There's no X for C. CX is equal to 0, and there's no X for F, right? So I would just have AX plus BX. Sum of the forces in Y is equal to 0. Here I've got A has no Y, B has no Y. F, its Y component is 318.2. And I have a CY that is unknown, plus CY, right? So immediately here, I can get that CY is equal to negative 318.2 newtons. Okay, so sum of the forces in Z is equal to 0. What I get here is AZ plus BZ. F, I've got a Z component, which is negative 318.2. And then I also have a component CZ. Okay, so I'm getting there, right? I've got one thing here, and that's interesting. So I'll make use of that. All right, now folks, I want to get into the sum of the moments expressions, and I'm actually going to go ahead and write that out first, and then I'll do a little bit of math to solve, because what we wind up doing after that is just that, it's math to solve. So I'm going to use this little quadrant here just so you guys can see everything. So I'm going to look at some of the moments, and I'm going to be strategic about where I take this. You can do almost anywhere that you want to, right? I could pick any one of these points, but it would be nice if these points, a point that I picked just made the math easier for me, right? So my feeling on this is that we should sum the moments about 0, because when we do that, these these reaction forces, while they're unknown, they're on planes, right? So they're acting along a particular axis, which is super easy. And I can really clearly see from the diagram what the moment arm is going to be. You may have a different opinion. You could sum the moments about A. These two would drop out, right? But you'd have to deal with F in its component form. And sum the moments about P, B, or you could sum the moments about C. Your call. But I'll do it about O. You may have a different opinion. So the way this is going to work is we'll start off with sum of the moments about O is equal to 0. And I'm going to do this in vector form. So just reason it out with me, okay? So I'm summing the moments about this point here, right here. F is going to drop out. That's not going to contribute, right? So I'm going to start by recognizing that I have a negative 300J, right? This guy I'm going to pull in right away. Then AX, so AX is going to cause, AX acting away from O here. The moment arm is going to be this whole length, and it's going to cause a positive K moment. So I would get plus AX, and the moment arm in this instance is 1.2 K hat, right? So I'm here to here, 1.2, 0.8 plus 0.4, and it's AX is acting in this direction. It would cause a positive Z spin, right? Okay, now let's deal with the other component of Z. So in this instance, I would get a negative Z is pointing up. I would get a negative I hat, so negative AZ times, again, the moment arm is 1.2 I hat. Now let me deal with the components from B. I'm going to get kind of the same thing, but a shorter moment arm. So I would get plus AX times, in this instance, the moment arm is 0.4. I'm sorry, that should be BX times 0.4, BX times 0.4, BX, EX times 0.4, K hat, minus, I'm going to start a new line, BZ times 0.4 I hat. And then C. Okay, so for C, the Z component in this instance is going to cause a positive I hat, or positive J hat moment. Right? So I would get CZ times 0.6. That's the moment arm coming back. J hat. Now for the Y component is going to cause a negative Z twist, right? So I would get minus CY, again, the moment arm is 0.6 K hat. Okay, that seems like a lot, right? Seems like a lot, but we're going to break this down to its components on each, in each direction. So some of the moments about O in the X direction, I'm just going to look at the I components now, right? I get negative 1.2 AZ. That's this guy, minus 0.4 BZ equals 0, right? So that's going to simplify into 1.2 AZ plus 0.4 BZ equals 0. Some of the moments about O in the Y direction, I'm just going to look at the J components. I get negative 300 plus 0.6 CZ. So I can go ahead and solve that for CZ, and when I do that, I get CZ is equal to 500 newtons. Cool. Some of the moments about O in the Z direction is going to give me just the Z components, 1.2 AX, 0.4 BX, minus 0.6 CY. CY we already know, right? CY we know from over here. That's negative 318.2. So this gives me an expression, and I had my math wrong earlier, so let me actually get this right, which is 1.2 AX plus 0.4 BX is equal to, negative times negative is positive, but I'm moving it on to the other side of the equation. I would get 318.2 times 0.6, negative 190.9. Okay, so gang, I want us to recognize at this point that all we have are a system of equations, right? We just have a system of equations, and let me write them. So Cy and Cz I already know, and those are my two unknowns at C. So all I'm left with is a system of equations that's a 4 by 4, right? So I have my sum of the forces in x is equal to 0 is ax plus bx, which is going to give me bx is equal to negative ax. Sum of my other expression here for ax and bx is this guy. Sum of the moments about O in the z direction gives me this expression, 1.2 ax plus 0.4 bx is equal to negative 190.9. So I can plug in for bx negative ax. So that's 0.8 ax equals negative 190.9. Ax is equal to 190.9 divided by 0.8 gives me 238.6. That's a negative 238.6 newtons, which means that Bx is just the negative of that is 238.6 newtons, positive 238.6. Cool. All right, now I also have expressions for, let's see, AZ and BZ, right? So here I've got sum of the forces in Z is equal to 0 is equal to AZ plus BZ minus 318.2 plus CZ. CZ I already solved for. CZ is 500, right? So that is going to give me AZ plus BZ is equal to negative 500 minus 318.2, negative 181.8. Okay, now I've got another expression for AZ and BZ, which is sum of the moments about O in the x direction gives me up here 1.2 AZ is negative 0.4 BZ, or AZ is equal to BZ negative 3 AZ. So I can plug that back in. BZ negative 3 AZ. So that gives me negative 2 AZ is equal to this. AZ is equal to 181.8 divided by 2, comes out to be positive 90.9. BZ is equal to negative 3 times that, 272, negative 272.7. All right, let's just summarize now, shall we? Okay, so let's write this out neatly. So our reactions we're asking for the reactions at A, B, and C. Sorry, there we go, reactions at A, B, and C. We're going to get, for our reactions at A, we have a force, which is AX. AX I solved for here, negative 238.6 in the I direction. The Y direction is 0. And the K direction here, AZ, is plus 90.9. K, and these are all in newtons. B is equal to BX. BX is 238.6 I, positive. Again, plus 0 J, minus 272.7 K hat newtons. C is equal to, in this instance, Cx is going to be equal to 0. Cy we solve for up here, that's negative 318.2 J, and CZ we solve for here, plus 500, whoops, K newtons. Cool. Just to cement this, I might also say MA is equal to 0, MB is equal to 0, and MC is equal to 0. So I've got a force in each instance, but my moments are equal to 0. That's what I got for the answer, guys. Okay. So again, it's a lot, right? But it's mostly getting everything correct up here, recognizing how many equations and how many unknowns you have, and then the rest is just math to solve. Okay, cool. Shall we do another? Let's. Okay, our next one is a problem that's just a little bit more straightforward. All right, I'll let you take a look at that for a sec while I get myself situated. What we're asking to do, it's some sort of tower, let's say. It's 5 meters tall, that's supported by a single cable. This cable runs over a pulley that's sort of in the middle of this tower. We're not given the weight of the tower, so we're going to assume that that's 0. And then we got this single cable running down. Then there's 2 forces acting on the top. They're both 5 kilonewtons. So let's see what we can do about this. So determine the reactions at A and the tension in the cable connected at B. Okay, let's work through this together, guys. So given the diagram, what we're being asked for is the tension in the cable T, and also the reactions at A. So let's first kind of think about what we know about this situation, right? A is a ball and socket joint, right? So that is not going to support a moment in any direction, but it is going to have a reaction force in every direction. So I already know that there's going to be an AX, an AY, and an AZ, right? This cable is obviously going to, as a cable, it's always going to be in tension. I may want to think strategically about how I'm going to draw my free body diagram when I'm dealing with that, okay? So the first thing to recognize here is actually that the free body that I want to draw separates this system through A and B, but leaves this pulley internal to the system. So I'm pretty much going to look at this as one whole system. I'm going to draw kind of a line around it. This whole system, not worrying about what's happening around this pulley. The pulley's just merely serving to redirect the force, and I have conveniently a vertical force there right along the y-axis. So if I were to draw a free body diagram of this situation, I'll draw something that looks like this, and I'll kind of have it come out and be sort of like a sheet, right? We're going to pretend we don't know what's happening there. And down here I've got a single force T, right? That's the tension in the cable where I cut it off. And here is point A, and at A I'm going to have an AZ, an AX, and an AY. And I'll draw all of those in the positive direction, X, Y, and Z. Up at the top here, I have 2 forces that are both 5 kilonewtons in magnitude, and I also know their direction. Okay, so that's my system. That's my system there. So let me recognize a couple things. So I'll start with the sum of the forces statement. Some of the forces are going to be, I'll call this guy actually F1 and this guy F2, and I'll make that T as a tension, and we'll just call this force A. Sum of the forces is equal to A plus F1 plus F2 plus T, right? But if I break this down into sum of the forces and X is equal to 0, what I've got here is, first off, I have a reaction AX drawn in the positive direction. Then I have the X component of this force, right, which is going to be 5 5 kilonewtons cosine of 30 degrees, so plus 5 cosine 30 degrees. This guy is going to be negative x minus 5 cosine 30 degrees. So these guys are going to cancel each other out, which gives me ax is equal to 0. Okay, so actually this ball and socket joint doesn't need to have a reaction in x because these two are perfectly balanced from each other, and this tension over here isn't contributing anything in x. Okay, so that's an interesting finding to begin with. Sum of the forces in y is equal to 0. What I'm going to get here is ay. T is purely in the z direction, right? This is purely just pulling up, so there's nothing in y there. Then each of these forces, F1 and F2, the y component is going to be in the same direction. So I would have 5 sine 30 degrees, and that's actually a negative, right? So it's in the negative y direction. Negative 5 sine 30, negative 5 sine 30 degrees. So AY is going to be 10 sine 30, or 5. AY equals 10 sine 30 is equal to 5 kilonewtons. Cool. Making some good progress here. All right, sum of the force in the z direction is equal to 0 is equal to AZ. Important thing to notice, F1 and F2 are purely acting in the xy plane, so there's no z component there, so that's going to be 0. So the only thing that's left is a t, and that's a minus the tension, right? So the tension is pulling down in this here. This would be 0I, 0J, negative T, K, right? That's what that force is, so negative T. So here in this instance, we get AZ is equal to T. So if I can figure out what T is somehow, I can figure out what AZ is. All right, cool. That's some of the forces. Now we have to think about some of the moments. So in taking some of the moments, again, I can take it about any point. I can take it up here. I could take it about B. I could take it about A. I'm going to take it about A just because, again, it wipes out all 3 of these unknowns. 2 of these unknowns I already know, right? So it's not that much of a gain. Really, I have a choice between T or A. With T, I'd have to account for this AY somehow. Actually, AY would pass through there, so not really. But I'll do some of the forces in A. Let's do that. Some of the moments about A is equal to 0. And I want to notice a couple things about this. So if I break this down into some of the moments about A in the z direction is equal to 0. In z, it would be a spinning about z, right? So I would be spinning about this axis. So A, basically in z, T is in the z direction, so that's not going to contribute a moment. And the 5 kilonewton forces both intersect through this line of action, right, through the z-axis. So they're also not going to contribute a moment. So inherently, because all forces either intersect or are parallel to the z-axis, this statement is trivial, right? There's nothing contributes a moment here. So that doesn't help me out at all. Some of the moments about A in the y direction, so I'm looking about spinning about y. The only thing that would spin about y, so here basically the t sits on the y-axis, so its moment contribution would be 0. The only things that would contribute to spinning about y would be these 2 forces, and they're symmetric about the y-axis. Therefore, they would also basically it winds up being a trivial situation there too, right? So this doesn't help us out at all with solving. So the 5 kilonewton forces are symmetrical about, this axis, right? So their contribution for spinning about y, they're both pulling an equal amount, which in this instance, right, I could go ahead and find those moments and everything, but I know what the values are here, and I know that they must balance each other out, right? So I'll say they're symmetrical about y. So that doesn't help me out in solving for t. So what will help me out in solving for t is some of the moments about the x-axis, right? About the x-axis. Sum of the moments A about the x-axis is equal to 0. That's going to give me 1.5 times t, and that's a positive moment, right? So, I'm sorry, negative movement, negative 1.5 times t, right? So this pulling down at a distance of 1.5 around this axis. And then these guys up here are going to contribute. The x component doesn't contribute, but the y component does in each instance. And that y component is actually, for both of these, going to be the same 5 meters away, right? So it's plus 5 meter moment arm times the component is 5 sine 30, right? Or this component here, the y component. In both cases, it's going to be a positive moment, 5 times 5 sine 30. And then there's another, right? 5 times 5 sine 30, because there are two of these forces acting here. So when I do this solves for, I have an expression just in t. I can solve and find t is equal to 16.7 kilonewtons, right? And we knew that AZ is also equal to t, so that means A is equal to 0I plus 5J, and then AZ is equal to T plus 16.7 K kilonewtons. All right, so there's the answer there. Thank you guys. That's all I have for you on 3D moments. A little bit more tricky math, okay, but it definitely can be done. Thanks.